Good evening. Your Excellency, Salim Al-Qubaisi, Director General of the Office of the UAE Space Agency, Chancellor, Vice Chancellor Mariette Westerman, Provost Arlie Petters, dear friends, dear colleagues, I'm thrilled to welcome you all to the first public lecture for the academic year 2022-2023 at the NYU Abu Dhabi Institute. Since its inception in 2009, the NYU Abu Dhabi Institute has provided a platform for exchange about the newest developments in research and scholarship across the disciplines. The Institute offers the NYUAD community, Abu Dhabi, the UAE, and the region opportunities to hear the world's foremost experts talk about their research and its societal relevance, technological and cultural impact, and importance for the world at large, ranging from artistic and creative innovations to issues of equity and inclusion, public health, and environmental sustainability, among many others. As a hub for vibrant, scholarly public engagement, the Institute is unparalleled in the region. This year's fall program offers an exceptional diversity of talks and conferences, including lectures on physics, heritage, history, politics, architecture, and many, many others. The invited speakers will discuss topics of local and global relevance. We firmly believe in the crucial role we play as we strive to bring together academics, experts, and leaders from around the world to address the community with open, first-hand knowledge. This year, we are also introducing 3 year-long lecture series on the following themes: the history and heritage of Al-Andalus, the environment in the Middle East, and philanthropy. Additionally, the Institute will highlight the UAE's 50th anniversary book by hosting key actors in this momentous endeavor. We look forward to see you among us as often as possible. Tonight, we are proud and grateful that the Physics Nobel Laureate, Art Mcdonald, will be launching our cycle with a lecture entitled Understanding Our Universe from 2 Kilometers Underground. We look forward, sir, to being enchanted and gratified. Thank you very much, Professor MacDonald, for being with us tonight. I will now give the floor to the Dean of Science at NYU Abu Dhabi, Professor Dean Marta Losada, who will introduce the speaker. I thank you again for being here. Enjoy the evening.
Good evening, everyone. It is truly my pleasure and honor to be able to introduce Professor Art Mcdonald. Art Mcdonald was born in Nova Scotia, Canada. He has degrees in physics from Dalhousie University and Caltech, his PhD. He also has, in addition, 15 honorary degrees. Following his doctorate, he worked as a research officer at AECL Chalk River Laboratories from 1969 to 1982. Then he was a professor at Princeton University from 1982 to 1989. He then returned to Canada, to Queen's University in that year of 1989, and worked as a professor until 2013, when he became Professor Emeritus. During this tenure, he held the University Research Chair 2002 and 2006, and the Gordon and Patricia Gray Chair in Particle Astrophysics 2006 to 2013. He was director of the Snow Institute from 1991 to 2003, and again from 2006 to 2009. An associate director of the Snow Lab Institute from 2009 to 2013. Since 1989, he has been the director of the Sudbury Neutrino Observatory's scientific collaboration. Among the many awards that he has received, he is a Companion of the Order of Canada, a co-recipient of the 2015 Nobel Prize in Physics with Dr. Kajita of Superkamikande Experiment. In addition, with the SNO collaboration, he received the 2006 John C. Polanyi Prize and the 2016 Breakthrough Prize in Fundamental Physics. He continues to be an active researcher in neutrinos and dark matter. As director of the SNO collaboration, Art was instrumental in the conceptual and physical design of the project and in the eventual data taking and analysis phases of the experiment. It was for his work and leadership in the SNO experiment, leading to the discovery of new properties of solar neutrinos, that Professor McDonald was awarded a Nobel Prize in Physics. Please.
Thank you very much, Marta. It's really an honor for me to be here to speak to you this evening. My wife Janet and I have been here for 2 days, and we have been, and it's our first visit to Abu Dhabi, and we've been very impressed with Abu Dhabi itself as a place and as education as a part of the cultural fabric of this community. And we have been blown away today, I would say, by this university, by how it sort of emerged full grown and now is a very active university and is providing students with opportunities in many different disciplines. And the facilities here are very, very impressive as we walked around and saw them today, as are the staff that we had a chance to meet with. And so it's been a very enjoyable visit so far, and I hope I can catch your interest a little bit this evening with the sort of things that I'm involved in, which have a substantial overlap actually with the work in the physics department, attempting to essentially understand our universe as completely as we possibly can. In our case, we have had the advantage of going deep underground in Canada in a very active nickel mine, which enabled us to have a location 2 kilometers underground in such a way that the phenomenon in Canada, which I didn't ask, but I'm not sure you ever see northern lights here. I don't think so. These are what happens. This is what happens in the atmosphere in Canada due to particles from various sources in outer space impinging on the atmosphere and making the atmosphere glow. This is a particularly spectacular example of it in Sudbury. As it happens, there's the smelter that takes the ore from the mine. That is something that we avoid because we're looking for very rare signals. We have a laboratory which is one of the lowest radioactivity, if not the lowest radioactivity location ever created, by having both great depth to have the rock remove those particles that are causing the atmosphere to glow like that, and also by being ultra clean everywhere. The whole laboratory, which originated with the SNO project, which you see here and which we'll talk about, and it's shown here, and then later, starting in 2003, an expansion to other areas that are principally being used to study dark matter these days, by having a location where we can present materials of different kinds for dark matter particles that we know exist. At least one model for what is happening in our galaxy is that there are particles that can strike our detectors as we pass through them in our galaxy, and as a result, perhaps we can, for the first time, see directly what the form of these particles is. Otherwise, they're only known because of their gravitational effects, and we'll talk a little bit about that as well. Having this very low radioactivity environment enables us to see, for example, neutrinos, particles that are able to penetrate through the rock with no problem, at a rate of roughly 1 an hour, making a faint burst of light in our detector. And from that, we're able to understand how the sun burns. We can understand what's happening in the core of the sun. We have the opportunity, by studying dark matter, to see why the Milky Way galaxy has this sort of spiral shape. We can understand the effects of dark matter in various scales of the universe, where it has had an impact on the generation of galaxies and stars. And we even can understand neutrinos coming from the Earth that come from the uranium and thorium that is contained within the Earth and provides about 40% of the heat flow out of the Earth. And so we can do many things. We can study how stars like our sun burn and create the elements from which we are made, which has implications also for fusion power here on Earth. We can understand the basic laws of physics, and in fact, by studying neutrinos in detail, we have been able to find the first a bit of information that goes beyond what has come to be known as the standard model for elementary particles. And we can understand what the composition of our universe is, because it is thought that there's about 5 times as much mass in dark matter as there is in the type of matter from which we are made. And so it's a significant component, both from the point of view of particle physics, because we don't know how it fits in our theories, but also from the point of view of cosmology, the study of the evolution of the universe, because it has a significant impact there. And so that's a description of how we deal with things on the largest scales, but we also attempt to understand the properties of particularly neutrinos in the first place, and eventually dark matter, where we really don't know how it fits in. And that's with the basis being a model that has worked phenomenally well in other circumstances, known as the standard model of elementary particle physics. It's the one that received a lot of attention when an important part of it, the so-called Higgs boson, was discovered at the Large Hadron Collider Accelerator at CERN recently. The picture we have of what things look like in the most microscopic level that we know yet describes our microscopic universe is this one, where the neutrons and protons that form the nucleus of an atom, where electrons go around that nucleus and form the characteristics of atoms, are formed from quarks, up and down quarks, rather prosaic names for them. We also know that related to these are particles like electrons, which are much lighter than quarks or neutrons and protons, and neutrinos, which are even lighter and which only occur in very rare circumstances, the rare forms of radioactivity, or in nuclear reactions that power the sun, where literally billions of them are even going through all of us right now as we sit here, and we never will experience them. Perhaps once in your lifetime, one neutrino will change one atom in your body into something else, and you will never notice it unless maybe at the time it happens, it hits you in your eye, and your eyes are closed, like many eyes are usually in my lecture by the time I get to this point. So then you might see a little burst of light, like, as we do in our detectors. But neutrinos are outside of normal experience, but they're quite profound in terms of their effects in the universe, and in terms of our ability to use them to understand parts of the universe that are beyond our understanding. And so most of what we're familiar with in terms of ordinary matter, as we refer to it, comes from this column, what we call a generation of particles, the quarks. There are also 2 other generations that have been identified quite clearly in higher energy events either from cosmic radiation or from the highest energy accelerators. They are very similar to the particles, the quarks here in this generation, but more massive typically and separate in their properties. The addition to this, each particle has a matching particle made of antimatter, which is something also that's typically outside of your experience, except if you have heard of, or in fact perhaps experienced, what's called positron emission tomography. It's a way of doing medicine, and one of the examples of how understanding particle physics at a very basic level enables you to apply it for the benefit of mankind. A positron is the antiparticle for an electron. If a positron is emitted by a radioactive source, and then it finds an electron, it annihilates with it, leaving only energy, which, because it annihilates at rest, it forms gamma rays that go off in opposite directions. And the way in which positron emission tomography works is you put a radioactive material that emits positrons in somebody's bloodstream. You then put detectors around their head, for example, if that's what you're studying, and you look at events where a gamma ray goes in opposite directions. This is relevant to what I'm going to say later on, because we think in the early universe, energy went in the opposite direction. An enormous amount of energy at the time of the Big Bang resulted in producing equal amounts of matter and antimatter, energy converted into that combination. We don't know why we don't have large amounts of antimatter in our universe right now. We don't know why this is a matter-dominated universe. But the properties of neutrinos may give us an opportunity to understand that. There are theories as to how that could, in the early universe, result in the sort of matter-dominated universe that we now live in. And so neutrinos become very important in terms of being able to understand such things. This is the microscopic scale. Let's start with neutrinos and neutrino experiments in order to understand how we use those neutrinos in our measurements, and particularly the Sudbury Neutrino Observatory experiment for which the Nobel Prize was awarded. Neutrinos, as you see, are the basic particles, and we always say that as far as we know right now, they're the basic particles. We don't know how to subdivide them any further, but scientists are always careful to say this is as much as we know right now. It may be that there's a structure inside any one of those particles that may be discovered in the future. But they're the basic as far as we know right now. They come in three flavors, as we call them, electron, mu, and tau. And they are not expected to switch between flavors. They only feel the weakest of all the forces, the weak force, and therefore they can pass through an amount of lead corresponding to the distance that light travels in a year, with only a 50% chance of hitting anything and stopping. That's because they don't stop unless they hit either the nucleus of an atom or one of the electrons going around it. If they do, then they have a probability of stopping. And so that's wonderful if what you're trying to do is to get them out of the sun in order to understand the reactions that are powering the sun, which is what we were trying to do in part of our experiment. But it also makes them extremely difficult. And so we ended up having to build a detector the size of a 10-story building in order to detect one an hour, as I mentioned earlier on. The standard model said that they should not change from the type produced in the sun, electron neutrinos, and the energy of the processes in the sun is only enough to produce that type of neutrinos. They should not change from that type to the other types, according to the standard model. If they do change to the other types, it implies that they have a mass which is greater than 0, rather than always traveling at the speed of light and having a mass of 0, which is what was in the theory before our measurements. So to do this, we built a detector which is, as I said, the size of a 10-story building. That person in the picture there is in fact to scale. It's 34 meters high and the cavity is 22 meters in diameter. We used a material called heavy water. Turns out that 1 in 6,400, I think it is, of the water molecules that you drink every day is heavier than the others because there is in the nucleus of hydrogen an extra neutron and makes it deuterium oxide, or D2O, rather than H2O. And that was important in terms of the measurements we were trying to do. It's very expensive. It's a part of the, it's non-radioactive, but it's a part of what's used as a moderator in the Canadian style of nuclear reactors. And so we were able to borrow, amazing to us at the time, $300 million worth of it for $1. Now that's a good deal in any economic environment. We did have to pay $1 million extra insurance in order to put it underground, but nevertheless, we were able to obtain it. And it is contained in the center of this detector, which is a gigantic acrylic sphere. This was the largest cavity ever excavated at this depth, which is quite extreme, 2 kilometers. And this is the largest acrylic sphere that was ever created at the time in the 1990s. Some of the techniques learned in doing this by the companies we were working with now result in aquaria that you will see in various places that are quite spectacular in their size and scale. And it has, that technology has developed in such a way, and oftentimes technology is driven by basic science, but ultimately produces things that are quite wonderful in terms of human experience. So in the middle is this heavy water. We want to see these faint bursts of light, and so we surround it with 10,000 light sensors, photomultiplier tubes as they're called, PMTs in our parlance. And this is, to give you the scale here, the diameter of the acrylic sphere is 12 meters. There's inside the photomultipliers about 1,700 tons of water and 5,300 tons outside, and a liner here. It makes it waterproof and also prevents radon gas from uranium decay in the rock from getting into the detector, because the whole objective here is to have a very minimum amount of radioactivity. And so we go from about a part in a million uranium and thorium in the walls of the cavity. And in fact, that's roughly true of almost anything. The floor here, about a part in a million uranium and thorium. In the middle, it's lower by a factor of 10 to the 9th. And we purified the water to be about 10 to the 9th, or 1 billion times more, less radioactive in uranium and thorium than ordinary tap water. It was a major engineering exercise as well as a physics experiment. And you can see here the scale of that engineering exercise. We had to do it in this mine in ultra clean conditions. We had to have air that was 10,000 times cleaner than the typical mine air. And everybody took a shower when they came in, as you do in producing semiconductor detectors or computer chips, and then put on lint-free clothing. So 70,000 showers during the construction. And you can see the acrylic sphere was fabricated from about 120 pieces that were scaled to be able to go down in the elevator, or as we call it, the cage, for the mine. And so once we had it completed, then we were ready to observe neutrinos in a process that looks essentially like the following, where a couple of atoms come together and fuse, emit a neutrino in the process in the core of the sun. This is one. There are billions of them being emitted. They pass through the solar system. They head for Earth. This happens to be headed for Sudbury. Pass through the Earth without any problems, get past the mine, and get to the point where they come into our detector and make a burst of light. And that burst of light is what we're looking for. But by having heavy water, we have the opportunity to have 2 different types of bursts of light. The first one is very explicit to the type of neutrinos that are produced in the sun. electron neutrinos. And the eventual signal for it is a cone of light. It's kind of like a sonic boom in electromagnetic radiation. And it's distinctive of that particular reaction. We have a second reaction, however, where any of the neutrino types, electron, mu, or tau, are capable of breaking apart the deuterium into a neutron and a proton. And that neutron we detect in 3 different ways that we can distinguish from the first reaction. And therefore, by looking at these 2 reactions, we can tell if electron neutrinos are all of the total neutrinos reaching you, or whether, for example, the first reaction is only 1/3 in terms of numbers of electron neutrinos compared to the total, which is what we actually observed. And so what we found is that we had a measurement that was very clear that neutrinos had changed from electron neutrinos into the other neutrino types as observed by the second reaction. And by looking at all the neutrinos coming from the sun, we were able to test the theory for the energy generation in the sun simply by looking at that second reaction. But we had to be careful because uranium and thorium can produce gamma rays that are energetic enough that they can enable that second reaction to take place, mimicking what a neutrino would have done. And so we had to be very careful. We had to purify the water to the point that in terms of uranium and thorium decay, we had 1 radioactive decay per day per ton of water in the detector, extremely pure water. But in doing so, we were able to get the following results. Now this graph shows you a projection of what's called the neutrino flux. It's the number of neutrinos per square centimeter per second reaching the Earth of the type that we were studying produced by a particular reaction in the sun. This is what the models predict in terms of the total number of electron neutrinos produced in the sun. This is what we measured with electron neutrinos, only about 1/3 of the total. On the other hand, when we measured all neutrino types, including the electron neutrinos that had turned into mu and tau neutrinos, emphasized by this crosshatched region here, we found that it matched very well with the calculations of neutrinos produced in the sun. We were able to make measurements that showed that there's only one chance in 10 million that electron neutrinos were not changing into other neutrino types. 5 standard deviations is the term that's used in particle physics for a discovery, and that's what we did. So what did we actually accomplish by doing this? Well, by building this lowest radioactivity location, observing only 1 neutrino an hour, but doing it for about 10 years, we could prove that neutrinos change from one type to another and have a finite mass, requiring changes to the standard model in terms of how neutrinos fit into that model. And this is what the Nobel Prize was awarded for. But it also validated the calculations of the production of neutrinos in the core of the sun, which are very similar calculations to what is done in order to calculate what the processes will be in nuclear fusion power reactors here on Earth, where the attempt is to create the fusion of elements similar to the ones that are producing these neutrinos in the sun, confined by magnetic fields instead of being confined by gravity as they are in the sun. And so it's a validation that the calculations that are being used for a very practical purpose here on Earth are in fact correct under the most extreme conditions, which is very, very difficult to validate otherwise. And so from that point of view, it's an example of how basic science can contribute, as I said earlier, to human value. But it also proved what we observed, that neutrinos are not the dark matter that we'll talk about in a moment, that fills the spaces between the stars when you look out on a starry night. Dark matter particles behave differently than any particle that's ever been observed in the laboratory, including neutrinos. They're much heavier, we think, than neutrinos, if in fact it is particles that are describing it. And this led to the establishment of Snow Lab, going beyond the original Snow experiments, in order that we could study more completely this phenomenon of dark matter by using the same sort of conditions as we created for Snow. So let me switch from what I've been talking about, and let me talk a bit about dark matter. But first, let me motivate this a little bit by talking about cosmology, talking about the Big Bang theory, and not this Big Bang theory. I was invited at one point, it's one of the perks that this Nobel Prize created. I was invited by the technical consultant for the Big Bang Theory program, which unfortunately is now off the air, although young Sheldon is doing a great job of picking up. David Salzberg actually worked for us in the summer when I was a professor at Princeton, and he invited me to come and be Geek of the Week, which meant standing around with the writers as the show was being presented. I didn't do anything, but if I was Stephen Hawking, I might get on the show, but I'm not. But the way they do it is they film it, and if there's a live audience, if it doesn't get a laugh, then the writers rewrite that joke and try it again. Anyway, it was a fascinating experience, and so let's get more serious. This is, in fact, our concept these days of what the evolution of the universe is since the Big Bang. We really don't know what happened before the Big Bang, and we don't know, in fact, at that time, which is an enormous amount of energy having been deposited in a very small space. We don't know some of the mechanisms associated with it, although we know an awful lot more in the last 30 years than we knew before that, and a lot of the information coming from wonderful measurements being made by satellites, physics experiments on satellites. The space program has contributed significantly, and we've made some contributions also through the underground experiments, unusual measurements that haven't been made before. So let's talk about how this is thought to occur. There is this enormous explosion followed by substantial inflation, as it is called, followed by an expansion thereafter. And this all occurred on the order of 13.5 billion years ago. It says 15 over here, but that's since been updated. So in this initial explosion, there's been enough energy. You'll notice the temperature inferred at that time, 10 to the 27 degrees Celsius, which is, I won't comment on Abu Dhabi weather, but you're better able to experience it than I am as a Canadian, let's say. In a very short period of time, all of that array of particles, as far as we know, was created through energy being converted into matter and antimatter. Subsequently, after about a microsecond, 10 to the minus 6 seconds, things have cooled off enough, only 10 to the 13 degrees Celsius, such that quarks can combine into protons and neutrons. After about 3 minutes, you have the formation of atoms, but only after about 300,000 years do you end up with the electrons combining with the nuclei formed here to produce neutral atoms. And at that point, the light can shine through. And there's been a remarkable set of experiments, particularly most recently from the Planck and the WMAP satellites, that show the distribution of light that exists as we can measure it today from that particular period, 300,000 years after the Big Bang. That's followed by a period where one can know about galaxy formation, which is strongly influenced by dark matter and by neutrinos, and that is about 1 billion years after the origin, and so about 12 billion years back in time, which is a sort of motivation or part of the motivation for the James Webb Space Telescope that has recently been launched and which appears to be a very successful exercise, and will be objective, for example, for the Square Kilometre Array in South Africa in future. So there's still a big question, as I mentioned, and that is, what about this matter-antimatter asymmetry? Where's all the antimatter gone? And so one of the things that we are attempting to do is to, and have come a long way, and we're almost finished in terms of repurposing the snow detector to measure something called neutrinoless double beta decay. In this case, what you want is to pick an element which has the possibility of 2 beta decays occurring without any neutrinos being emitted. And that then, if you can get enough of this material, and by replacing the heavy water with a material called liquid scintillator that gives you 100 times the light output, you can then observe a phenomenon. And in order to do that, we had to make major renovations to the snow detector. It's now running with this liquid scintillator installed, and we're preparing to install the tellurium over the next 2 years. The process is that the so-called beta decay, where one electron and one neutrino are emitted, in this case, you can do it for nuclei that are separated by 2 atomic numbers, and then you'll get, similar to what you get from ordinary beta decay, a continuum of energies if you sum the energy of the electrons. And that's because the neutrinos are carrying away some part of the energy and they go in different directions, and so you get a continuum. If no neutrinos are emitted, which can happen if neutrinos have certain properties, and you sum up the energy of the electrons, then that is a peak, which you see here at the end. And that's what these experiments seek to measure. And there's an enormous set of experiments internationally that are seeking this. One of the ones that will be among the most sensitive is the so-called Snowplus Experiment. This can only happen if neutrinos are their own antiparticle, if there isn't any difference between the two other than perhaps their spin, which is a quantum mechanical property. And that is a property that fits very well in the theories of how this process of antimatter decaying in the early universe can work. They're daunting experiments because the lifetimes that are involved in this rare radioactive process that would lead to this peak are in excess of 10 to the 26 years. So, but if you think about Avogadro's number, if you remember from way back in school, 6 times 10 to the 23 atoms in a molecular weight of a material. If you get tons of material, you can get a fair number of atoms there, and then you can wait for 10 years or so and see if something decays. But you really need to get rid of anything else that can produce a signal in that region. And then hence being underground in the lowest radioactivity laboratory in the world is absolutely a prerequisite for doing this type of experiment. And if we are capable of doing this for a signal that is at the limit of current measurements, we would see a signal that looks like this. This red sitting on, this is the signal from the end, the tail of that continuum, and this is other radioactivities that are suppressed rather substantially. We think we can get a sensitivity on the order of something less than 100 milli-electron volts, or 0.1 electron volts, which is almost 1 million times smaller than the mass of an electron. And so it really is a sensitive experiment. And it's sort of the ultimate recycling process with the whole experiment being reused. So now let's talk about dark matter and how it can influence things. The measurements that were made of this so-called cosmic microwave background, the light left over from the point at which the light began to shine through, have really been exquisite, made with the experiments such as the Planck satellite. In addition to that, there are a number of other indications of the fact that there is dark matter in our universe. It makes up about 5 times as much mass as the matter that we're made of. This is just to show you that you see this line, this blue line, that goes through these data points, which are averaged as the red points. You can see the data points scatter around a bit, but this is the average. And it matches almost perfectly for a model of the universe that includes about 25% dark matter content in the universe. And that would show up in a difference in this particular peak in this spectrum. The model fit to this data is really one of the remarkable achievements of science, and the Nobel Prize has been awarded for that. We think it's weakly interacting as well, and this is sorry, I missed one slide. Let me go back for a moment. Why do we think it's around us? Well, if you look at our Milky Way, I'm pushing the wrong slide. I'm not pushing the laser, I'm pushing the slide changer. Let's try it again. There. If you could see our Milky Way galaxy side on, which typically you don't when you look out at the sky, you're seeing that pancake side on. And so it's a band of stars across the sky. But if you could see it side on, and many other galaxies look of a similar type, then it kind of looks like a spiral, like this. And if you measure how fast the stars are as you move out from the center, the ones, this is a plot of the data, the ones that are the farthest out in radius, which is plotted along the axis here, this is their velocity, the profile looks like that. Well, if you asked if it's just this glowing matter that's holding them in their orbits, pulling them in like swinging a bucket of water over your head and holding onto the string, that gravitational force would not be enough to hold them in that pattern. You need 5 times as much other material, which is referred to as a dark matter halo. And using general relativity, you can also observe similar things by looking at how the light from galaxies is distorted by dark matter in front of them. And again, very similar results. We think it's weakly interacting. One piece of evidence for this is the fact that here's a picture of two clusters of galaxies that have managed to pass through each other. The red or the pink here being the ordinary matter measured by X-rays, the blue being the imaging of it for the dark matter content. And what's observed is that the dark matter passes right through the other matter, apparently not observing any effect from it. And so we end up with this model for the universe as a whole, which has 4% us, 4% ordinary matter, 26% dark matter, and 70% another form of what is referred to as dark energy, which was inferred from the fact that you were lied to in high school. That is, gravity is not always an attractive force. There is a small repulsive component that is measured by measuring supernova, for which you can determine exactly how much light was produced by this supernova, and you can therefore determine the distance simply by how much reaches you from such a large distance, just a fraction of the total emission that gets to you. And secondly, by measuring how fast that supernova is moving by measuring what's called the redshift, shift into light due to the velocity away from you. If you do that and you plot it up, you find that after the Big Bang, things have not just accelerated according to what you would expect from gravity as an attractive force, but there's a small component that is accelerating it. And as a result, you can translate that into an energy component, and that makes up the other 70%. So we know that dark matter is a substantial part of our universe. We know that it exists in our galaxy from those rotation curves I described to you, and now we're trying to see if we can observe it directly by letting it hit various types of detectors in our laboratory. And so this is what our laboratory now looks like. Originally, it was just this component over here for the SNOW project. The expansion produced 4 or 5 new sites for experiments, and it was designed to attract people from outside Canada to come and work with Canadians in a program the Canadian government put forward and that financed this, this laboratory. There are now a number of experiments that are collaborations between Canadians and international groups. As I said, most of them aimed at dark matter. And interestingly, they are experiments that present the atoms at which the dark matter is to hit in different forms. The one I'm going to describe to you is the Deep 3600 experiment that uses argon. There's another one that uses helium. Another one here that's just starting uses germanium and silicon, and others somewhat smaller that use silicon. And this one uses fluorine. We also have Snowplus looking for something very different. And it's all, the whole laboratory, ultra clean, better than class 2000, and very low fluxes of neutrinos. So this, I mentioned Stephen Hawking earlier. Stephen visited us twice underground. This is about 1 year before he passed away. He was adamant that he really wanted to see this laboratory and what's happening with dark matter, and so we didn't require him to have a shower when he got underground, but we vacuumed him off on the surface, and he came down in a special car in his wheelchair. But absolutely remarkable individual. WIMP detection is a matter of presenting an opportunity for a WIMP to interact with a nucleus, causing it to recoil just like a billiard ball on a table when hit by the cue ball. Our passage through the galaxy, plus our seasonal effect of going around the sun, gives velocities that make it possible to make measurements of that interaction producing a burst of light. Argon has special properties that if that burst of light comes from a nucleus recoiling, it's emitted in 7 nanoseconds, a billionth of a second, whereas for light produced by radioactivity, it's emitted in 1.7 microseconds, about 500 times longer. And so we simply digitize all our pulses, and we can get rid of the radioactivity and throw them away. This is what the detector ends up looking like. It's pretty similar to the SNOW experiment in that there's this inner sphere here which has light sensors attached to the outside of it. And just to show you the lengths we go to try to deal with radioactivity, the final thing we did was to insert this sander. There are rotating discs on either end, and it lifts up so that it's inside this tube in order to get through the long tube to get to the detector. Then it opens up and it rotates around to cover the entire inner surface and take about 0.5 millimeter off it. And so you end up inventing technology to do your physics, and this is a clearly obvious one. Now, after having made sensitive measurements with the DEEP experiment with 3 tons of liquid argon, we've now joined with scientists from, you see the list of countries there, about over 400 scientists from around the world, to build the next largest experiment at about 20 tons, active volume out of 100 tons total. And we are planning to, the collaboration is planning to move to the next generation at 400 tons for the ultimate experiment. We're using a technology that was developed at CERN for a detector that's going to happen at SURF, underground facility in South Dakota, where the beam being shot from the Fermilab accelerator, referred to as the Dune experiment, to provide an outer vessel filled with liquid argon, and then there is a inner vessel inside this. This is what it will look like in the Gran Sasso laboratory underneath the Gran Sasso mountain in Italy. And here we not only look at the light, we also put an electric field on and drift the electrons produced until we get an added signal at the top of the detector. It's called a time projection chamber. And once again, we're using acrylic as an ultra-pure material in order to try to avoid radioactivity. Technological development, we're going to have 21 square meters altogether of what are called silicon photomultipliers, a new type of photomultiplier that have potential application, for example, in improving positron emission tomography by reducing the amount of radioactivity you have to use such that it's not dangerous to use it at that level for assaying children. And so, again, pushing things for basic science results in pushing technology of value to humankind. They have remarkable properties. They're very low on radioactivity as well. In order to do the experiment, we need ultra-low radioactivity argon. It turns out that argon that comes from a carbon dioxide stream used to pressurize oil wells in Texas, which the carbon dioxide stream comes from Colorado, and we have identified that it's 1,400 times lower in one of the radioactivities that's produced by cosmic rays in the atmosphere, so that we can use it in this new experiment, DarkSide. We're going to do that. We're going to purify it in a facility that's almost complete and has tested very well in Sicily, size of the Eiffel Tower, in order to make it ultra pure, and then eventually we'll then send it to the actual experiment in Gran Sasso, a little bit east of Rome. So, what can we do with this? Well, this is a summary, and it's a complicated figure, I realize, but let me just try to interpret it so you get a feel for where we are. This is the sensitivity for the interaction of a dark matter particle with a nucleon inside an atom, inside the nucleus of an atom. And the lines on here that are solid indicate that no dark matter particle with an interaction probability anything above that line and a mass corresponding to this range here could possibly be an interaction that is similar to what's observed for dark matter in the gravitational information, in what happens in our galaxy and so on. And slowly, as we build bigger and bigger detectors, we're improving this sensitivity. These lines go down to, for example, the xenon experiment, which people here are working on, has the potential in the next few years of having a sensitivity which is almost a factor of 10 better than sensitivity so far. Our experiment is similar to that. to that, and ultimately this 300-ton experiment will get even further. Our problem, ironically for me, where the most important element of the experiment I got the Nobel Prize for was detecting neutrinos. Neutrinos are the background that we can't deal with any further in this experiment. You can't shield them out, even if you went very deep. I mean, neutrinos pass right through the Earth with no problem. They will be a problem in limiting these experiments. However, the theorists trying to understand where dark matter particles are going to show up as an extension of what we already know, say it's quite reasonable to try to think of particles that only interact with this sort of strength, sort of probability of interaction at this sort of mass. We're also having complementary experiments at the Large Hadron Collider. We are observing dark matter particles that were produced in the original Big Bang. They are attempting to produce them again for the first time since the original Big Bang, but they have to have enough energy to be able to do it. You'll see that, you know, their sensitivity peters out at around this energy. Ours extends beyond that, and we also have certainly greater sensitivity in terms of the ability to observe the interaction with matter. So that's what I wanted to tell you about today. And we're, in summary, we have a much more complete knowledge of our universe from the smallest to the largest scales. And that has come from a combination of astronomical measurements and other measurements such as the ones we do in underground laboratories. There are a number of fundamental questions still remaining to be answered. Having an extremely low radioactivity background in your laboratory is providing excellent conditions for doing this, and we're addressing very fundamental questions. But we're also using cutting-edge technology, and that's a strong underlying resource that's valuable for society's needs. Now, you just got, I think the term that's often used is attempting to drink from a fire hose in terms of the amount of information that I threw at you. And following the Nobel Prize, I was interviewed many times on TV and so on in Canada in terms of attempting to understand what did you actually do. And there's a comedy program in Canada that watched me trying to make these explanations and wrote a script and contacted me and said, would you be willing to read this script for one of our skits on our program? And so you'll recognize some of the things in this that I presented in the process of the talk, but I understand that Tim Hortons actually exists here in Abu Dhabi. Is that correct? How many people in the audience have ever had a Timbit? Fair number. They're the little donut holes that Tim Hortons sells, and they come in different flavors. Neutrinos, of course, come in different flavors as well. So just for fun, to see if you can recognize the difficulties I have in explaining this topic in this particular skit.
It's an illustrious list, including Lester B. Pearson, Alice Munro, and now a guy from Cape Breton. Physicist Art Mcdonald is Canada's latest winner of a Nobel Prize. Here to explain why he's the best in the world at what he does is Art Mcdonald.
Hi, I'm Art Mcdonald. I'm a Professor Emeritus at Queen's University, originally from Cape Breton, and I attended Dalhousie University. And I'm a co-winner of the 2015 Nobel Prize in Physics. People from 22 Minutes have asked me to come in and explain what I and our team did to win this prize. We demonstrated that the flavor of neutrinos produced in the core of the sun, electron neutrinos, changed into one of the other two flavors, muon and tau neutrinos, as they traveled from the core of the sun to, okay, I'm being told I have to make it simpler. Neutrinos are very basic subatomic particles that we don't know how to subdivide any further. And okay, they're asking me to dumb it down a little bit. A subatomic particle is smaller than an atom. Atom is a unit of matter. Really? You don't know what matter is? It's 7. Okay, neutrinos are like Timbits. Sometimes they're like chocolate, sometimes they're like cherry-filled, and sometimes they're like the old-fashioned glaze. I must be the first person that ever won a Nobel Prize in Timbits.
So the important message is science is fun. It really is. And it also can be very practical. So thank you very much.